In the previous video, which is part 1 of the series, I introduced the importance of dams and how geotechnical engineers are involved in embankment dam construction. This is part 2 of a 3-part series, and we are going to cover the geotechnical aspects of gravity dams. This is Clement. I hold a master's degree in civil geotechnical engineering, and welcome to Geotechs with Clement. So, what is a gravity dam? A gravity dam is a dam constructed from concrete or stone masonry and designed to hold back water by using only the weight of the material and its resistance against the foundation to oppose the horizontal pressure of water pushing against it. Of course, the ideal and most economical site location should have a suitable foundation for the dam, and the width of the river at the dam site should be minimum so as to keep the length of the dam minimum. In order to provide a large basin for the reservoir, the site should open out upstream. Before we dive deep into the foundation and the geotechnical aspects of the gravity dam, it is important to understand the forces acting on the dam. Most, if not all, horizontal and vertical external forces acting on the gravity dam, that is, the potential to destabilize the overall stability of the dam, are transferred to its foundation. This goes without saying. Water pressure is one of the most major external forces acting on the gravity dam. The horizontal water pressure exerted by the water stored in the upstream side of the dam is simply calculated from a simple hydrostatic pressure distribution diagram. In the case of gravity dams with an inclined surface on the upstream side, a load of water over the inclination is also presented as a vertical force acting on the dam. The water pressure is separated into two cases. One case is without downstream water and the other has one. The downstream water is known as the tailwater, which acts to a certain extent as a counterforce to the upstream water. Because of the permeability of the foundation materials, water seeping through the pores and the fissures will exert an upward force on the base of the dam. If this uplift force is not properly monitored and controlled, it will develop and compromise the overall stability of the structure. In earthquake-prone areas, the gravity dam will be heavily subjected to ground movements. During an earthquake, the waves produced are capable of shaking the dam in every possible direction. The effect of an earthquake is equivalent to imparting an acceleration to the foundation of the dam in the direction in which the wave is traveling at the moment. The earthquake waves induce forces in both horizontal and vertical directions. When water is flowing in the river upstream, it picks up some loose pebbles, soil, and vegetation. These suspended particulates are deposited at the base of the dam, forming a thick silt layer. This silt exerts a horizontal force on the dam. If the upstream face is inclined, the silt, which is supported on the slope, will also act as a vertical force. Waves generated on the surface of the reservoir by blowing winds cause a horizontal pressure towards the upstream side of the dam. This pressure is heavily dependent on the height of the wave. In cold climate regions, water on the surface of the reservoir freezes and expands. The dam face then has to resist the force exerted by this expanding ice. This force acts linearly along the length of the dam and at the reservoir level. The dam body exerts by far the biggest vertical load on the dam foundation. It is the most important force, particularly for gravity dams. The stability of the dam largely depends upon this force. Now that we have established the forces acting on the dam, which are then transferred into the foundation, let's go ahead and discuss the geotechnical aspects of the foundation, potential foundation failures, and the associated foundation treatments implemented by geotechnical engineers on these amazing structures. To begin with, the foundation of the dam should be relatively free of major faults and shear zones. Foundations with too many defects require expensive foundation treatment programs, which increases the project cost. A geologic investigation is required to determine the general suitability of the site and to identify the types and structures of the materials to be encountered. A handful of ground parameters have to be determined and recorded in a site investigation report. As we all know, the ground is comprised of different geologic materials with different minerals and physical properties. It is important to determine for each material the shear strength of the intact portions, the sliding friction strength of discontinuities, and the shear strength at each interface with a different material. This includes the strength at the interface of the concrete and the material exposed on the completed excavated site, the permeability of each material, and the deformation modulus of the foundation. The ideal conditions for a gravity dam will be an incompressible hard rock, durable and perfectly impervious, without any discontinuities which the gravity dam can be founded on, and have a perfect lock and key to resist the loads and prevent it from sliding, rotational, piping, and settlement or compressional failure. However, the real conditions of a geological site may say otherwise. The site usually has faults, seams, carbonaceous rocks, crush zones, and loose overlying soil, which compromises the stability of the dam and the foundation. The imperviousness of the foundation is very important to minimize seepage flow in both soil and rock foundations. When the foundation consists of pervious sands and gravel such as alluvial deposits, two possible problems exist. One pertains to the volume of seepage, and the other is concerned with the forces exerted by seepage flow. The forces exerted by water as it flows through the foundation can cause an effective reduction in the weight of the soil at the toe of the dam and results in the lifting of the soil. If uncontrolled, these seepage forces can cause a progressive erosion of the foundation, often referred to as piping, and allow a sudden collapse of the structure. The uplift pressure is increased under the conditions of high seepage, and this pressure acts on the dam foundation interface or between the bedding planes of the foundation rock. Following the collapse of the Sella Zebino Dam in 1935, different causes were blamed for the disaster, including instability due to the uplift force. The engineering team did not consider the effects of uplift force during the design of the dam, even though it was clearly stipulated and required by the technical standards of that time. The design of erosion, seepage, and uplift control measures requires extensive knowledge of the type, stratification, permeability, homogeneity, and the properties of the foundation materials. To mitigate the seepage flow, some of the control measures that can be implemented include installation of impervious aprons and cut-off walls upstream and downstream. The introduction of these elements changes the flow net, therefore changing the flow channel. You see, if we take an individual water particle, we can theoretically predict its flow path in the foundation under the structure. The collection of these water particles exerts a horizontal and a vertical force. The installation of an upstream apron or a cut-off wall increases the length of the flow path and therefore reduces the horizontal seepage and uplift forces on the dam body. Just as a side note, the addition of drainage systems at the base and body of the dam to transfer water downstream helps in the reduction of the uplift pressure. In theory, the idea behind a dam is to stop and accumulate a huge body of water. However, water carries a huge force. Therefore, the idea is that the net horizontal forces acting on the gravity dam do not exceed the frictional resistance produced between the body of the dam and the foundation. If the frictional forces is less than the horizontal hydraulic forces, sliding failure occurs. The resistance may be due to the friction alone, or it may be due to a combination of friction and the shear strength, depending on how the dam was constructed. The foundation or portions of it must be analyzed for stability whenever the structural configuration of the rock is such that direct shear failure is possible, or whenever a sliding failure is possible along the faults, shears, and joints. Associated with stability are problems of local overstressing in the dam due to the foundation deficiencies. The presence of such weak zones can cause problems under either of the two conditions. when differential displacement of the rock blocks occurs on either sides of the weak zones, and when the width of the weak zone represents an excessive span for the dam to bridge over. Sliding failure may result when the rock foundation contains discontinuities and horizontal seams close to the surface. Such discontinuities are particularly dangerous when they contain clay, bentonite, or other similar substances that drastically reduces their frictional resistance. On September 30, 1911, Austin Gravity Dam, also known as the Bayless Dam in Pennsylvania, USA, collapsed. The main engineer openly admitted to some of the foundation construction misjudgments. In mid-January 1910, a warm period combined with rain caused a snowmelt that filled the reservoir behind the Austin Dam within 3 days and the activation of the spillway for the first time. On the next day, the dam slid downstream on its foundation, deflecting 18 inches at the toe and 31 inches at the crest and cracking in several places. Though divided, the dam remained anchored to its foundation rock. However, the foundation was poorly constructed and the rock layers slid over each other. To mitigate such foundation problems during the lifespan of the gravity dam, foundation treatment methods most compatible with the geologic conditions and the dam design must obviously be implemented. Consideration of geologic features through the comprehensive geotechnical investigations conducted throughout several phases of the design and the construction of the dam will ensure the most appropriate means of the foundation preparation and treatment at the site. Foundation treatment may include measures such as excavation of the low-quality rock, application of dental concrete or contact grouting, deeper treatments such as the installation of cut-off walls, foundation grouting, or the combination of the two, and the use of drains and filters at the base of the concrete dams. If you are someone who enjoys geotechnical or geological engineering content, please hit the like and subscribe button to show me some support. Thanks for watching. Peace.